Welcome back to AI.Code.Cast. Today we're diving into this classic puzzle, the next permutation problem. It's the kind of challenge that makes you think like, wait, is there like a clever way to do this? Or am I just stuck like trying every single possibility?
Oh, there's definitely a clever way. But before we get there, let's make sure we're all on the same page. You've got a list of numbers, let's just say 1, 2, 3 to keep it simple.
Okay.
And the permutations of this list are just all the different ways you can rearrange these numbers.
Anyway, so like 1, 3, 2 would be another permutation, and 2, 1, 3, like all of those.
Exactly.
Yeah.
But the next permutation problem, it's not just asking us to list out all the permutations. It's something more specific, right?
Yeah, it's gotta be.
It's like, imagine we're thinking of these permutations as words in a dictionary.
Okay.
So 1, 2, 3 would come before 1, 3, 2 in that dictionary order. And what we're trying to find is that lexicographically next greater permutation, the one that comes right after our current arrangement.
Okay, lexicographically next greater permutation. That's a lot of words. But I think the dictionary thing helps.
Yeah.
So for 1, 2, 3, the next one would be 1, 3, 2 because it's like a little bit bigger.
Precisely. Now, how would you go about finding that next permutation without having to list all the possibilities?
Well, my first instinct is always just brute force it. Try everything.
Yeah.
But I have a feeling that's not going to be very efficient, especially if we have a longer list of numbers.
Yeah, you're absolutely right. Brute force would mean generating every single permutation and then comparing them to find the one that's like just a tad bigger than our starting point.
Oh, yeah.
And remember how we talked about permutations growing factorially?
Oh, yeah.
With a list of just 10 number, you'd have over 3.6 million permutations to check.
Okay, so brute force is out the window. We need a smarter solution, something that like takes advantage of the structure of the problem.
Yeah.
What we think about it like finding the weakest link in a chain. There's got to be like a point in the sequence where we can just make a small change to get a bigger permutation.
You're on the right track. What if we start by looking for the first place, reading the numbers from right to left where the sequence stops decreasing?
Okay.
That point where we see a number smaller than the one before it, that could be crucial.
Okay, interesting. So in our 1, 2, 3 example, we wouldn't find that breaking point until the very beginning because the whole sequence is increasing. But what if we had something like 3, 2, 1, the very first number, the 3, that's like the weak link.
Exactly. We call that the pivot. It signals a place where we can potentially swap things around to create a bigger permutation.
All right, so we found the pivot, the place where things start to get interesting. But what do we do with it? What's the next step in this clever solution?
Well, if the pivot is where we need to make a change, then we need to figure out what to swap it with.
Okay.
Think about the numbers to the right of the pivot.
Okay.
Can you spot a number that's just slightly bigger than the pivot value itself?
So in 3, 2, 1, if the 3 is our pivot, we need to find something in the 2, 1 part that's bigger than 3. There's nothing there. Does that mean we need to look at the entire sequence?
Good catch. You've stumbled upon an important detail. In this case, where the pivot is the very first element and the rest of the sequence is descending, it means we've already got the largest possible permutation. The next permutation is actually the smallest one.
Okay.
Which means we just need to sort the entire sequence in ascending order.
So it's like wrapping around. If we're already at the biggest arrangement, we just go back to the beginning. Okay, that makes sense. But what about cases where the pivot isn't the first element?
That's where the real magic happens. Let's take a slightly more complex example, maybe 1, 3, 2. Where's the pivot here?
Let's see. Going from right to left, the first number that's smaller than the one before it is the 3. So the 3 is our pivot.
You got it. Now to the right of the pivot, do you see a number that's just slightly larger than 3?
Okay, looking at the 2 part. Well, the 2 itself is bigger than the 3. So I guess the 2 is what we'd swap the pivot with.
You're on fire. By swapping the 3 and the 2, we've created 1, 2, 3, which, if you think about it, is indeed a bigger permutation than 1, 3, 2. But are we done yet? Is this definitely the next permutation in our lexicographical order? We're close. But there's one crucial step we're missing. Remember, we want the very next permutation in that dictionary order. Right now, after our swap, we have 1, 2, 3. But what if there were other permutations that started 1, 2 and have like a slightly different arrangement for the rest of the numbers?
Oh, okay. I see what you mean. Just swapping the pivot isn't enough. We need to make sure the numbers after the pivot are also in the right order to give us that like smallest possible increase.
Exactly. Think about the portion of the sequence to the right of the pivot.
Okay.
In our original example, 132, that portion was just 2. After the swap, it's still 2. But what if our original sequence was something like 13542? What would happen after we swap the 3 and the 4?
Okay, so we'd find the pivot to the 3, and then we'd find the 4 to swap it with, giving us 1, 4, 5, 3, 2. I see the problem. The 5, 3, 2 part isn't in the right order to give us the very next permutation.
Exactly. To guarantee that we get the correct next permutation, we need to sort the numbers to the right of the pivot in ascending order. Think about it. Before we swapped anything, the numbers to the right of the pivot were in descending order.
Right.
Oh, yeah, that's because the pivot was the point where the sequence stopped decreasing. So by reversing that descending order, we make it ascending and ensure that we're not, like, accidentally skipping any permutations in our lexicographical journey.
Precisely. So in our 1, 4, 5, 3, 2 example, we'd reverse the 5, 3, 2 part to get 2, 3, 5. Our final next permutation will be 1, 4, 2, 3, 5.
Okay, I think I've got the steps down. Find the pivot, swap it with the smallest number to its right that's bigger than the pivot, and then reverse the part of the sequence after the swap point. It's like a little 3-part dance move for numbers. A very elegant dance move. And the beauty of it is it works incredibly efficiently. We're only making a single pass through the sequence to find the pivot and the swap candidate, and then just a few more operations to reverse the tail end. No need to generate millions of permutations and compare them.
So we've cracked the code, so to speak. But how would we actually express these steps in a way that, like, a computer could understand? I'm thinking about our listeners who might want to try implementing this algorithm themselves.
You're thinking like a true coder. Well, we don't need to get into specific programming languages, but we can outline the steps in a more general pseudocode kind of way.
Perfect. Let's break it down. First, we need to find that pivot. How would we describe that step in pseudocode?
We could say something like, start at the last element of the array and work backwards. Compare each element to the one before it. The pivot is the first element that's smaller than the one before it.
Okay, that's clear and concise. Okay, next up, finding the swap candidate. How do we describe that process?
We can say, starting from the element after the pivot, scan toward the end of the array. The swap candidate is the smallest element that's still larger than the pivot value.
Got it. And finally, the reversing step. How would we write that in our pseudocode?
We can put it simply. Reverse the portion of the array starting from the element after the pivot to the very end of the array.
There we have it, the next permutation algorithm in all its pseudocode glory. But before we move on, I want to make sure we address a potential pitfall that tripped me up earlier. What happens if the pivot is the first element and the rest of the sequence is already in descending order?
Excellent point. You're referring to cases like 3, 2, 1. If the pivot is the very first element and the remaining elements are in descending order, it indicates that we're already at the largest possible permutation.
Right.
In this scenario, the next permutation is actually the array sorted in ascending order, effectively wrapping around to the smallest permutation.
Right. It's important to remember that edge case. Otherwise, our algorithm might get stuck in an infinite loop or produce incorrect results.
Precisely. So to handle this, we need to add a condition to our pseudocode.
Okay.
Before searching for the swap candidate, we should check if the pivot index is 0 and if the rest of the array is descending. If so, we simply sort the array in ascending order and return the result. Otherwise, we proceed with the regular steps of finding the swap candidate and reversing the subarray.
Okay, I think we've covered the core algorithm and even identified a potential pitfall and how to handle it. But this is AI.Code.Cast. We like to go beyond just like solving problems and think about the bigger picture. Where could we actually use this next permutation algorithm in the real world?
Well, imagine you're building a scheduling system. Like, let's say you need to find the most efficient order to complete a set of tasks. Like taking into account things like deadlines and dependencies.
Oh, so you could use the next permutation algorithm to like explore all the different orderings of the task and see which one leads to the shortest overall completion time or like the least amount of wasted resources.
Exactly. Or think about ranking systems, like the algorithms that decide everything from like search results to recommendations on like your streaming service.
Yeah.
And as new data comes in user preferences, ratings, you might need to recalculate the rankings, finding that like next best arrangement based on the updated info.
That's a fascinating application. Like the next permutation algorithm could be a key part of keeping those rankings dynamic and responsive to real-time changes.
Yeah.
Like constantly searching for that like slightly better arrangement.
Yeah.
Making small adjustments to optimize the whole system.
Precisely. It's a subtle but powerful concept.
Hmm.
And beyond those examples, I can even see applications in fields like cryptography, where you might need to generate a sequence of keys or passwords that follow a specific pattern but are still unpredictable.
Oh, that's a cool idea.
Eh,
Like the next permutation algorithm could be used to create variations on a base key, ensuring that each new key is like both valid and different from the previous one.
Right.
It adds a layer of complexity without resorting to completely random generation.
Exactly. It highlights the versatility of this algorithm. It's not just a theoretical puzzle. It's a tool that can be applied creatively to solve real-world problems across all these different domains.
This has been such an eye-opening deep dive into the next permutation problem.
Yeah.
We went from understanding the basic concept to dissecting this elegant single-pass solution, and then even explored potential pitfalls and real-world applications.
Yeah. It's a perfect example of how algorithmic thinking can unlock new possibilities and provide really efficient solutions to problems that seem complex.
Huge thank you to all our listeners for joining us on this journey through the world of permutations and algorithms. We hope you've learned something new and maybe even sparked some ideas of your own.
Keep those algorithmic minds engaged, and we'll catch you on the next deep dive into AI.Code.Cast.